Okay, so reaction mechanisms. Now it sounds just like it should be, I guess, that a mechanism. A mechanism like in a cuckoo clock could be like, okay, this spins this goes to this, and then we produce this, all right? So that's the same thing with reactions. One reaction happens, another, till we finally all together have a bottom line. So the process by which a reaction occurs. Sometimes we can create like something, a product in 3 steps. Maybe we need 4 steps. Maybe we need 5, whatever. All those processes that we go through, each reaction is part of the mechanism. So it describes in detail the order in which the bonds are broken. It's basically a recipe for chemistry. So there are elementary reactions. Those are the single step events. So each one reaction is called an elementary reaction within the reaction mechanism. So every single reaction is part of being the bigger part. Okay. Molecularity is something we're going to talk about, and that is just the number of molecules that participate as reactants in an elementary reaction. It is not tough, guys. It is unimolecular if there's just one single molecule. And you are looking at coefficients, so we'll talk about that in a sec. Bi is obviously 2 reactants. And ternary, termolecular, is when you have 3. Okay. Most of the time we don't go too far beyond that, but that's what we're going to look at this time. Okay. You have multi-step mechanism, which means that sequence of each elementary 1, 2, 3, 4, whatever equations you have, you're going to be able to do that. We're going to go to our speedy check example in just a little bit, but here it shows you a couple ways that we could have different molecularities. So you still have 2, whether it's 2 of the same reactant molecules, reactant molecule and then another reactant molecule, or all kinds of different variations here. Okay, so A, B, and C are all reactants in those analogies there. All right, so when we talk about these, there are going to be different steps here, and then there's always going to be a rate determining step. A rate limiting step determines it. And again, it's kind of the common sense thing. Again, if you're running a relay, you're only going to be as fast as your slowest team. Okay, so that's going to determine your rate or your limit to how fast you can go. So you're only as strong as your weakest link. So we've done that a lot, and that is true in the real world. Like the slowest link is going to slow you down. Okay. So you'll normally be told, hey, here's the slow step, here's the fast step, or some kind of hints to get you there. But the slowest step will always be your rate determining step. Now, we're going to talk about a couple things when we go to our speedy check in a little bit. But here's a graph of some mechanisms. You can see that this is a 1, 2 step reaction. Every transition here represents a next equation. So we're going to look at that, and that is going to be pretty darn quick. Okay, and then we have what are called intermediates and some other things we're going to throw in here. All right, so we are going to turn to the back page of the speedy check, number 29. All right, so we're going to do number 29. This is, will a reaction actually happen or not, or is this a correct mechanism for this reaction? So this is the reaction I want. Okay, I know it's got scary things in it. That's what I want you to get over is it doesn't matter. The proposed mechanism is 2 steps. So you have step 1 here and step 2. And the first question says, is this proposed mechanism consistent with the overall equation? So is it going to work? So the first thing I would do is try here, this kind of Hess law-esque, okay, is I'm looking at what do I want in the end? Okay, I want MoCO6. Now that's not MoCO5. So I'm not looking at, oh, there it is, MoCO6, all right? These other ones, no. All right, they are not what I'm looking for. MoCO6 is already on the reactant side. There's only one of them, so far that's working. All right. Now this next one, PCH33, yeah, we have one right here. Look at that. It's even on the correct side. It's a reactant, right? So we're just seeing, does this work? So far, check. Let's go to our other side here, our products. We got this big, long, okay? We'll call it MoRara. Now, MoRara is right here. All right. So we see boom, 1, product side. All is really working out nicely. Isn't this fun when it works out? These are fun. And your CO are perfect. So this one looked hard to begin with, but it was like one of the simpler ones, to be honest. Now, what about this here? You didn't even want it, did you? So this is something you didn't want. So guess what happens? You gone. because they're on opposite sides, they're going to cancel. And so your answer to this is definitely yes. Okay? Because you can see my work. See work. Everything works out. So you're going to have to show that, crossing out the ones that don't belong. And even maybe you could dot, dot, dot. Yes, that goes there. Dot, dot, dot. That one fell in place. Whatever you want to do. But at least if they're the same colors like that, if you don't have the colors, again, we have them at the front of the room. You're always able to borrow those. And that's how that works. So molecularity, I'm going to stop there. Step 1, how many molecules are involved in step 1? Well, there's just one. So it's unimolecular because there's only one molecule. That is as easy as it goes. You're only looking at, the reactants. And then look at this one. We have 1 and 1, so that is 2, so that is bimolecular. That is as easy as molecularity is. Do not make it hard. And then intermediates, what's the intermediate? It means something that was involved in the 2 reactions but cancels out. So it's like a spectator, but it's not an ion, so we don't call it that. It's the molybdenum CO5. Okay, that was involved, but it wasn't in the end. All right. So the intermediates are going to cross off, if not in the final reaction. All right. And then this is the same type of problem I want you to practice on, number 30. And then 31, here is our lovely reaction progression of a reaction mechanism. And what's going to happen is you're going to see that we have all these transitions going in. We got 1, 2, 3. Each transition is there. So how many transitions do you have? They're each hump 1, 2, 3. You have 3 transition states. How many intermediates do you have? This says, based on the following reaction profile, how many intermediates are formed in the A going to D. So you have your reactants and you have your products. But what do we see in the middle? B and C. So you actually have 2 intermediates. They're B and C represented here. We don't know what that is. We just know that. Which step is the fastest? Well, you can tell this. Okay, I don't have to from the graph here. This step has this activation energy right here. This step has, and again, this is kind of eyeing it, but there will usually be one that kind of stands out. And of course, C all the way to D, that activation energy is going to take a lot longer, right? So that is going to be not very fast because you're going to have to get more activation energy. If you were to look at this, it's a little bit tough, but I would say that the second step, so B to C, is the fastest step, that second step. So we can just write these as A to B, this is B to C, and this is C to D. That's kind of how we write this out. Overall, is this reaction exothermic or endothermic? And we can ask a lot of questions, guys. We'll get into them as we go. But the bottom line is, where are my reactants and where are my products? My products are ending up lower, so that means we had to give off, and that's exothermic. So we'll read a lot of these and practice these, so ask questions in class.